Hello everyone, welcome to this lecture. The topic of discussion for today is going to be center of mass for continuous objects. So previously we saw the case of center of mass when we are applying it to individual particles, okay, and we had described our formula of position of center of mass as r, and it was given as 1 upon total mass and summation of all the particles, the product of mass times the position of those particles. Okay, and we also talked about the motion of center of mass. For example, you can consider a wrench, which is a complicated shaped object. If it is thrown uh, and tossed, it can do rotational motion, it can do vibrational motion, and it will do some translational motion going from this left hand side to the right hand side. And in this complicated motion, what happens is the center of mass position, which is given by this red dot, it has a much more simple and predictable motion. Okay, and the reason why this is happening is that the uh, acceleration at the position of center of mass is zero. Okay, so the velocity of the center of mass of the object is constant. Okay, and this happens when there are no external forces acting on the system. Okay, so we want to extend this idea now to include continuous shaped objects. Okay, when we apply some net force on an object, the net force will be equal to the total mass of the object times the acceleration of the center of mass. And this is valid because the center of mass behaves as if the entire mass of the object is uh, located at the position of center of mass. The formula for the position of center of mass gets modified, and the formula for continuous objects is of this form, that r of center of mass is given by 1 by total mass of the object integral of r times dm. So now you're considering an object of certain mass and you're integrating to get the entire mass of the object. Okay, and by intuition we can see that for objects such as sphere and for objects such as a cube, the center of mass will lie somewhere in the center of the regularly shaped objects. But for irregularly shaped objects, we need to do the calculations very diligently. Okay, so let's take this example where we have to hang a metal sign in such a way that the sign is hanging perfectly parallel to the ground. Okay, something like shown here. All right, and you have just a single wire through which you have to hang this sign. Okay, so to achieve this, we want to know where this position of center of mass of the object will be. Okay, and the question says that we have to find the distance from the left end and the top where we have to attach this wire so that the metal sign will be supported in such a way that this bottom of the sign will lie parallel to the ground. And this is a very practical problem. And again here, because of this object being a continuous object, we can use the formula that we had just shown, where we are trying to find the position of the center of mass by integrating over a certain volume. Okay. Okay, great. So what I was saying is, to solve problems like these, you have to use the idea of the relationship of density to your mass divided by volume. Okay, because in any solid, your mass can change, and accordingly your volume will change, but your density will remain constant. Okay, so what we are going to do is we are going to consider a small mass element dm. Okay, and this small mass element dm will have some width dx. Okay, so if you write the density of this small mass element, you will get the density is dm divided by the volume, which will be this dx times y times certain thickness of your triangular sign. Okay, and similarly you can write a general expression for your density as well. Like I said, density doesn't change. You can consider the entire mass, and then you have to consider the entire volume. Okay, so if we just represent the length on the x-axis as a and the length on the y-axis as b and the same thickness, then you can write the density as the total mass divided by total volume, which will be just 2m by a times b times t. Okay, and from here what you can do is you can get rid of this dm by writing it as density times this denominator function, right? And instead of rho density, you can substitute this general expression, okay, which is 2m by a times b times t. Okay, because you see the m is not changing, m is constant, so then it can come out of the integral. Okay, and again a and b are also fixed. Okay, t is also fixed for your situation, and then you're left with this expression dx. So you're integrating with respect to dx, so that is fine because you're trying to find something along the x-axis. Okay, and the other two terms are your y and t. Okay, so you can see that t and t are getting cancelled, so you get rid of the t and all you're left with is y. Okay, so you get an expression for dm as 2m by ab times y dx. Okay, and again this y and x are related to each other because if you see this slope on the horizontal, this this looks like a straight line, right? So what you can say is y at any point is related to x by the slope. Okay, which is just the difference between the y values by difference between the x values. Okay, that will be b by a. So with this expression, you can even get rid of y, and all you are left with something integral in terms of x dx. Okay, and now that is the integral that you can solve. Okay, so now to solve this integral, we can substitute that in. Okay, so we have the first term, which is r is just your x value, right? So we are trying to find along the x-axis. So this r will become your x value. Okay, so you should be comfortable with what we are speaking, right? R is a position variable, right? So if you are trying to find along the x-axis, the r becomes x. If you are trying to find along the y-axis, the r will become y. Okay, so the first term will become x. Okay, and the next term is dm. So you are substituting 2m divided by a times b, and for y, like I showed you, it is b by a times x times your last thing, which is dx, right here. Okay, so now you have your m and m will get cancelled. Okay, 2 is constant, it will come out. Again, a, b, and b by a, these are all constants. Okay, these are all measurements of the length, right? So they are constant in the system. So b and b will cancel, and a square will come out of the integral. Okay, so you get 2 by a square, and now you have an integral of x dx. So now you're integrating along x. So you're going from 0 in your frame of reference all the way to a. Okay, so your limits will become 0 to a, and all you're left with is x square dx. Okay, and integral of x raised to n is x raised to n plus 1 divided by n plus 1. So x square, the integral will be x cubed divided by 3. Okay, and now you have to just substitute the endpoints 0 to a. So you get 2 by a. So this should be square here. Let me make that correction. So this should be 2 by a square, right? And then you will get a cube here, and so a square and a cube, only a will be left. So you get that the value of position of mass along the x is 2 by 3a times, you should always write I so that you know which direction it is pointing. Okay, so it's a 2/3 value of this value of a. So if I divide this into 3 parts, 1, 2, along this line, I have to now attach my wire. Okay, but I don't know along y-axis which point. Will it be here or will it be here? I don't know. Okay, and of course it matters, right? Because there is a moment that will come into play if you attach at different points. Okay, so that's how you find the value for x of center of mass. Okay, so again let's look at how you can get the position along the y-axis. and now the expression will change. You have 1 upon total mass again, and now you're integrating from 0 to b, right? That's what you're doing along the y-axis, okay? Because the lowest value that you can get along the y-axis is 0, and the maximum value you can get is b. So you will do integral of y dm, and again we know the expression for dm. We had just shown it before in the previous calculation. So you can substitute this function in here, okay? So you have 1 upon m and y, and then you get 2m y divided by a times b times dx, okay? Again, 2 and a and b are constants, they will come out, okay? You get integral of y square, and now you have some dx, okay? So you are integrating y function with respect to dx, but you cannot do that straightforward, right? Why? Because y and x are interrelated to each other, so you have to change the dx variable to dy, okay? So you already know what y is. Y is just b by a times x, so dy, a small change in dy will be b by a. This will remain constant, it will be times dx, okay? So if I am substituting for dx, that will be just a by b times dy, okay? So again I am having two constants, a and a will cancel, okay, and b will come out, okay? I have already had a b outside, so it will be 2 by b square, and integral of y square dy, like before, it will be y cube by 3, okay? And then you are substituting the endpoints of the y, 0 and b, okay? So you get 2 times b cube divided by b square, and so you're left with 2 times b divided by 3, and then there's j, okay? So the complete expression for r would be 2 by 3 a I plus 2 by 3 b in the j direction, okay? And in this figure it would mean somewhere like here, right? So 2/3 value along this point along the a, and 2/3 value along the y-axis, okay? And so that is the point. So you have to drill a hole exactly here, okay? Take a wire and hang it on this point, and then sign will be horizontal along the ground, okay? The same idea, if you do experimentally, there is a technique which you can use, okay? So if you have an irregularly shaped object and you don't know where the center of gravity is for this object, all you have to do is you have to drill two holes, okay, at any points on an object, and you hang the sign from the first point, and then you will get this axis of symmetry, okay, on which the center of gravity will lie, okay? But you don't know which point it lies on. Then again you hang the object from the second hole, okay? So let's mark them so that it's visible what is happening here. This is point 1, so you will hang along the 1, and then you get this axis, so you can mark it on your object. Then you take and hang the object from 2, and then again you get this axis, and then where this two axes coincide, that is your point of the center of gravity, okay? So experimentally you can just drill two holes and you can hang an object, any object, and you can try to find the center of gravity. And you can do this at home as well. You can take just a irregularly shaped cardboard, okay, and just go ahead and be imaginative, and just make it very irregularly shaped in terms of, you can have a mass distribution of a cardboard. For example, you can have something like this, so most of the mass is concentrated on one side, okay? And now you are trying to hang this piece of cardboard by a thread, so you can drill two holes anywhere along this cardboard, and then you can mark the axis and try to find where the center of gravity is. So it's a simple home exercise you can do. Continuing along these lines, what we want to do is we want to now do a calculation for the center of mass of a uniform rod, okay? So what you see on your screen here is a uniform rod, okay? And we can again define our axis. So we will choose our frame of reference point to be 0 here, okay? And then we can say that this axis is your x-axis. We can say that this axis will be a y-axis, and we can follow the right-handed coordinate system and say that this is going to be a z-axis, okay? So again we have to consider that it's a uniform rod, okay? And let's say the length is L of this rod, all the way here. So this length is L. Okay, and now we want to find where the position of the center of mass is for this uniform rod. So anybody wants to guess where the center of mass for the rod will lie?
L by 2.
L by 2. That is a very good guess. So let's see how we can mathematically find that. Okay. So again, remember we were trying to find the position of the center of mass. So mr of the center of mass will be some integral of your value of r, and you are integrating over the mass. Okay, and again we have to use the concept of density, and since it's a you can consider a one dimensional case, and in that case we say that mass per unit length, which is represented as lambda, will be your m, which will be total mass of this rod. So let's define that total mass is m divided by the total length. Okay, so that is going to be your value for your linear mass density, okay, which is lambda. All right, lambda is also known as linear mass density. Okay, so for all one dimensional objects you can use this approach. Okay, and again, like we were doing before, we will consider a small mass element here. Okay, and this small mass element will have, let's say, a mass of dm. Okay, and let's say it has a width of dx, which is this length unit here. So has length dx, then again lambda, which is a constant property of this rod, will be your mass over your length. Okay, so you can substitute that in this equation here. So let's calculate this. The position of the center of mass will be 1 over total mass integral of, now you're integrating along this length. You have chosen this as your point of origin, so you are integrating from 0 all the way to L. Okay, so your limits are 0 to L, and R is your position along the x-axis, so R becomes x, and instead of dm we are now going to use lambda times dx. Okay, and we know what lambda is. Lambda is m over L, so you can write lambda as m over L, and those two are constant, so they can come out of the integral, and so you will have x times dx 0 to L. Okay, and here your mass will cancel, so you get 1 over L, and integral of x dx is x square by 2, and now you have to use the limits from 0 to L. Okay, and so you will get L square by 2, and you had 1 over L here, and now it is pointing in the I direction, which is the unit vector along this direction. Okay, so you get L by 2 I. Okay, so as we had predicted, the position of the center of mass is exactly in the center of this rod. Okay, and that would mean that if I just keep a finger here, or if I keep want to balance this rod on an edge, all I have to do is I have to move that edge at the center position, and that will just balance this entire rod, and this rod will not fall over. Okay, because that point where this L by 2 value is the point where all the mass is concentrated. Okay, ask what will be the center of mass for a hoop, you know, which is semicircular. So now I'm going to consider so again we have to choose our point of origin. All right, so for convenience I have chosen it to be in the center of this circle. Okay, and again I want to find my position of center of mass for this object. Okay, so I can define that, let it have a total mass m. Okay, and again this R position that I'm trying to find for this center of mass, right, from this origin, right, it can now be decomposed into the x and y directions, right, because it's a two-dimensional situation now. Okay, so we have this r variable will be some x in I direction plus some value of y in the j direction. Okay, and you can imagine here, suppose I'm calculating this r, which is the radius value for this hoop. Then on the y axis, right, if I look at the angle that this element makes, which is theta, you get that the y value is r sine theta. Okay, just by using your trigonometry. Okay, and again the adjacent side, which will be cos of angle, adjacent side by hypotenuse, will be r cos theta. Okay, so you can change the coordinates and write it in polar coordinates and say this m of r of the center of mass will be r cos theta plus r sine theta times j. Okay, and times your dm value. Okay, so again, now for dm, to progress further, what we need to do is we need to again define the density term. Okay, so again, let's consider a small mass element. Okay, and what we'll do is we'll integrate this over the entire mass, and then you will get the total mass. Okay, so if we take the small mass element dm, and let's say it has this width, which is the angular width as ds, right? So you get the mass per unit length. Again, this value is dm by ds for this small mass element. Okay, and by trigonometry, you know that this ds will be some r times d theta. Okay, whatever theta value it is covering, that is what this expression is going to be. Okay, so again, in a general expression for this entire hoop, you will have lambda will be total mass divided by the total coverage that it is doing, which is half of a semicircle, right? So it's half of the perimeter of a circle, which will be pi times r. Okay, so now we can substitute dm as lambda times ds in our expression here. Okay, and ds is r d theta, so you get lambda times r d theta. Okay, and again, now we are integrating from zero angle all the way to your angle of pi. Okay, 180 degrees. So when you move from zero angle to 180-degree angle, you are covering the entire perimeter of this loop. Okay, and from here on, it's pretty straightforward. You have r square. R square is the radius. It's a constant term. It doesn't change, so it can come out of the integral. You have 1 over m that is coming from here. Okay, you have lambda. Again, it's a constant value. It can come out, and what you're left with inside is cos theta plus sine theta and the coordinates I and j. Okay, so again, for cos theta and sine theta, it's easy to calculate the integral, because you know the derivative of sine is cos, so the opposite will be the integral. So cos theta will give you sine theta, and again you're integrating 0 to pi for the first term. For the second term, it will be minus of cos theta. Okay, again 0 to pi, and if you do that, uh, again this first term goes to 0, because sine of pi and sine of 0, both our terms are 0. And in the second term, you get basically 1 minus of minus 1, so you get basically 2 that comes out of here. Okay, and the negative signs, they cancel, so you get essentially the position of center of mass is 2r divided by pi, and it's in the j direction. Okay, because the I term completely goes to 0. Okay, so again, where is this value of 2r by pi? Suppose r value is 1. So if r is 1, I'm getting a value of 0.63. So it's a little bit above your center value of half, right? So somewhere around here, you see. So your position of center of mass is not lying anywhere on this object. It is lying just below the object. Okay, just because of this curvature. Okay, so that is your position of your center of mass. Okay, that it is along the y-axis. We have it's along the j. There is no I component, and the value is about 0.637 of your value of your r term. Okay, that's what 2 by pi is. Okay, so this is an example of a non-intuitive problem where we have to apply the same idea of density and substitute it in the equation and do some fancy integration to solve the problem. Okay, and later on you'll see we will be using this kind of technique again and again. Okay.